In 1918, the year that World War I ended, the Nobel Prize in Chemistry was awarded to Fritz Haber, the savior of German munitions and father of modern chemical warfare. It wasn't awarded for his contributions to human suffering, of course, but for describing a method to convert gaseous atmospheric nitrogen into fixed liquid ammonia. The choice was still controversial, but it stands as an excellent example of the moral dimensions that all scientists and engineers, and especially military scientists and engineers, must eventually confront. Nitrogen fixation is what's called a dual-use technology. It had immediate and important military applications, like allowing Germany to keep producing explosives and fighting the war, but it also has important civilian applications. Ammonia is a key ingredient in fertilizer and is needed in order to feed the population. As I said in this week's first video, the nitrogen compounds necessary for plant and animal life are relatively rare. The Haber-Bosch process supplies it in quantities that bacteria just can't, and has made agriculture at least 400% more efficient. It's been estimated that half of the nitrogen in your body comes from synthetic fertilizers. Put another way, this means that about half of the world's population owe their existence to the Haber-Bosch process and to Fritz Haber. Just as the Haber-Bosch process can be used two ways, its chemical equation can also go in forwards and reverse. We want to convert atmospheric nitrogen and hydrogen into ammonia, but the opposite process can also run. Ammonia can be turned into nitrogen gas and hydrogen gas. It's important to remember that both the forward and the reverse processes are happening simultaneously. Under a certain set of pressure, temperature, and catalytic conditions, one reaction might be happening at a faster rate than the other, but both are still happening continuously, working towards a state where for every single nitrogen molecule that's converted into two ammonia molecules, there are two different ammonia molecules transforming back into nitrogen. At that point, when the rates for the forwards and the backwards reactions are equal, this is what we call equilibrium. It produces a stable ratio of products and reactants. We can calculate the ratio by dividing the concentrations of the products by the concentrations of the reactants to get a constant, which we call K. We account for the stoichiometry of the balanced equation by raising the concentration of each species to a factor equal to its stoichiometric value. The amounts of product and reactant are directly related to each other. So if we remove some of the product, the reaction has to drive forward to reduce the amount of reactant left in the chamber. This is Le Chatelier's principle. As I said in the first week of this course, chemistry is a practice that people do. So even though nitrogen or ammonia don't have any intrinsic ethical dimension, the problems that scientists choose to address and the applications that engineers choose to serve most certainly do. The choices we make have consequences. Fritz Haber's choices had consequences on the global scale. Some of those were good, and some of those are not. Where that equilibrium rests really isn't for us to decide. All we can do is to remember our duty to respect the dignity of all persons in our search to learn more about our universe and to use that knowledge for the public benefit.